So this is the fourth lecture out of chapter 17. So in this lecture we look at a different mechanism for the reactions of aromatic compounds. And so this mechanism is what's known as a nucleophilic aromatic substitution. So NAS. So if we compare aryl halides, so this is an aryl halide, right, to an alkyl halide. Well, the aryl halide carbon halogen bond is stronger than the alkyl carbon halogen bond. So the leaving group is much harder to substitute than if it was on an sp3 hybridized carbon like it is here. That's sp3, whereas this is sp2. So the alkyl halides are in general more reactive. But for the aryl halide, you can substitute the leaving group off. So this would be an example. If you take bromobenzene with potassium hydroxide and water at 370 degrees Celsius, then you can substitute the bromine for the OH group. But that's pretty brutal conditions. All right, 370 degrees Celsius, most organic compounds would decompose long before that temperature is reached. But this reaction will work. So the question is it an SN1 mechanism? So if you remember how SN1 mechanisms work, right, the bromine would have to leave to make a carbocation, and then hydroxide would attack it, or water would attack it. But that carbocation is very unstable because putting the positive charge on an sp hybridized carbon is not a good place to put a positive. So no, this doesn't want to make the aryl carbocation. It's too unstable. Could it do an SN2 mechanism? Well, the answer is no, because to do an SN2, if you remember how SN2 reactions work, the nucleophile has to attack opposite the leaving group. And since the benzene is flat, the only way that would work would be for the nucleophile to go through the ring, and obviously that's not going to happen. So the mechanism for nucleophilic aromatic substitution is different than SN1 and SN2. And it's facilitated by electron withdrawing groups on benzene, so like nitro. So the nitro group is an electron withdrawing group, and it activates the ring towards nucleophilic aromatic substitution. So you want to be careful in this chapter. You don't want to confuse electrophilic aromatic substitution with nucleophilic aromatic substitution. So the nitro group deactivates the benzene ring towards electrophilic aromatic substitution, but it activates it towards nucleophilic aromatic substitution. So how do you know if it's a nucleophilic aromatic substitution? Well, that's electron rich. So it can act as a nucleophile. And so basically what nitro does, because of that positive, it pulls electron density out of the ring, and that's going to make this benzene ring more susceptible to nucleophilic attack. So the OCH3 can come in and kick off the chlorine. You only have to go to 85 degrees Celsius with this nitro group on the ring. So pretty mild conditions, and then you can do the substitution. In this case, you get a 92% yield. So some of the characteristics of this reaction, so the rate depends on both the nucleophile and the alkyl halide. And so unlike SN2, for nucleophilic substitutions, right, the best leaving group is fluorine, and then chlorine, and then bromine, and iodine. So fluorine's the best leaving group and iodine's the worst. But for SN2, that's exactly opposite, right? Where iodine's the best nucleophile, and then bromine, then chlorine, and fluorine's an absolutely horrible nucleophile. So we'll explain why the difference in just a minute. Okay, so the basic mechanism for the reaction. So how does this work? So you take a lone pair of electrons on oxygen and make a bond to that carbon, and take these two electrons in the pi bond and move them up to make a lone pair. So that's an addition step. And then in the so you make this intermediate, where aromaticity is lost, right? Because now you have an sp3 hybridized carbon where the oxygen and chlorine is attached. So benzene, of course, likes to be aromatic, so it's going to regain its aromaticity. These electrons come back down, remake the double bond, and kick the chlorine off. So that's an elimination. You're eliminating chlorine in this case. And so overall you do an addition elimination. It's a two-step mechanism. And then there's your product. All right, so why is alkyl fluorides faster? Well, what do you know about fluorine? It's the most electronegative atom in the periodic table, right? So it's pulling electron density out of the ring. And that's going to make the ring less electron rich, so it's going to be more susceptible to nucleophilic attack, and also that puts substantial positive charge density on that carbon, so that's going to make it attractive to a nucleophile. So in terms of relative rate, so if we had an alkyl chloride and let it do a reaction and assigned its a rate of 1, so the alkyl fluorides react about 300 times faster, and then the bromides and iodides react a little bit slower than the chlorides do. Okay, so how does the nitro group help? How does it facilitate this reaction? So in order to understand that, we have to look at the mechanism. And we have to look at the stabilities of the intermediates in the mechanism. Okay, so again, if we work through the mechanism, so take a lone pair on oxygen, make a bond to carbon, 2 electrons in that double bond become a lone pair on carbon. And so this is your intermediate. And we want to look at what stabilizes it. Right, well, what stabilizes it is resonance. So again, the more stable the intermediate is, the lower the activation barrier to make it, and so the rate of that reaction becomes faster. So how can the nitro group help? Well, let's start drawing resonance structures and see how the nitro can help. So let's take that lone pair, move it down this way. So we're going to move towards the nitro. So if we put a double bond there, that puts 5 bonds on one of these carbons. So we need to get rid of 2 electrons. So we're going to take that double bond and make a lone pair on this carbon beside the nitro. So that would give you this resonance structure. And now let's take that lone pair and move it here, and make a double bond between carbon and nitrogen, and then these electrons become a lone pair on oxygen. And so now we have delocalized that negative charge onto the nitro group. So this is the key resonance form. So that's the key resonance form of the intermediate, which illustrates how the NO2 group stabilizes the intermediate, because anytime you can do localized charge, that stabilizes the charge. And so if you make that intermediate more stable, again, the activation barrier to make it is lower, and so the reaction proceeds faster. Okay, so if we just wanted to finish off this mechanism, so we've illustrated how the nitro group helps, so now let's finish the mechanism. So we can take the lone pair electrons on oxygen, move it back down to remake that double bond. And then let's see, so let's move this double bond here and move that double bond there. And then we can take this lone pair electrons here and move it down to remake a benzene ring and kick your chlorine off, and there's your product. Right, so what we want to note, if the nitro group was meta to the chlorine, then it cannot stabilize the intermediate by resonance. Because if you notice where that negative charge is at, so with respect to the chlorine and the OCH3 group, it's here at the ortho position, or it's here at the para position. Well, I better not use a dot. We don't want to think that's a free radical. So it's there at the ortho position, or it's there at the para position, or that negative is at the ortho position with respect to the chlorine and OCH3, but it's never at the meta position. So if the nitro group was at the meta position, then you would not be able to draw a resonance form like this, where the nitro group can delocalize that negative charge. Okay, so here I illustrate. So this would be the resonance forms if the nitro group was at the meta position. So again, if we take a lone pair, move that there, and these electrons go here, and then keep moving that lone pair around, so that goes down, these go up, and if you notice that negative charge lone pair just skipped the carbon that the nitro was on, so the nitro will not be able to delocalize the negative charge. And then these go here, that go there, and then move these down here, and chlorine comes off, and there's your product if the nitro group was meta. So notice that the negative skips the carbon that the nitro was attached to, so the negative cannot be delocalized to nitro, which means the nitro cannot stabilize the intermediate, which means it's going to have a higher activation barrier to form it, which means its rate of formation, if the rate of reaction, is going to be slower than if the nitro group was at the ortho or the para position. So if the nitro was at para, you could find a resonance structure similar to this one, where you could illustrate the nitro group can delocalize the negative charge. So the point being, in nucleophilic aromatic substitution, the electron withdrawing group, nitro in this case, helps the reaction if it's ortho or para to the leaving group, but not if it's meta to the leaving group. Okay, so again, just to make sure you don't confuse the reactions. So NO2 is deactivating to electrophilic aromatic substitution. That will be the reactions that we talked about in 17-1 lecture, that first lecture. But it activates it to nucleophilic aromatic substitution. How much does it activate it? So if there was no nitro group on the benzene ring and you did this reaction and you assign that a rate of 1, with one nitro group, the reaction is 7 times 10 to the 10 times faster. With 2 nitro groups, it's 2.4 times 10 to the 15 times faster. And if there's 3 nitro groups on there, that reaction is too fast to measure. Okay, so that's another example of how things can help facilitate nucleophilic aromatic substitution. So if we compared these two molecules, where you have a pyridine, right, a nitrogen inside the benzene ring. So if you did this reaction with chlorobenzene and that assigned that a rate of 1, if this is pyridine, where the leaving group is next to the nitrogen, that reaction is 230 million times faster. Right, so how does the nitrogen help? So again, let's just look at the intermediate. So draw the mechanism. So take a lone pair here, make a bond there, and then these 2 electrons become a lone pair on nitrogen. So that's your intermediate, and so that's a good place to put a negative, right? So why is nitrogen a good place to put a negative? Because nitrogen is electronegative. And then in terms of finishing the mechanism off, we would simply bring that lone pair back down, remake your pyridine ring, and chlorine comes off. All right, so if we compared that to the nitrogen not being there, so if it's just chlorobenzene, so if that attacks here, that goes there. So negative on carbon, that's not a good place to put extra electrons because carbon's not very electronegative. So this intermediate is much more stable. Than that intermediate. So it's more stable, easier to form, activation barrier to form it is much lower, so reaction is much faster kinetically. Okay, so there are other ways to do nucleophilic aromatic substitution. So one is through what's called a benzine intermediate. So if you did this recipe, so if you took a chlorobenzene or bromobenzene or benzene with some leaving group on it, and reacted it with NaNH2, which is a very strong base, sodium amide. And the solvent is typically ammonia. So if you liquefy ammonia, so ammonia is a gas at room temperature, you do this reaction at negative 33 degrees Celsius, ammonia will liquefy. Okay, so then basically what happens in this mechanism is nitrogen's a strong base. What do bases do? Bases take hydrogens, right? So that pulls this hydrogen off. These electrons go there to make a triple bond, and chlorine comes off. So that's basically an E2 elimination at that point. And then you make benzine. So benzine is very reactive. It's not very stable. Right? Why isn't it stable? Well, what's the hybridization of these carbons? Right, those carbons are sp3 hybridized. Or, sorry, they're sp hybridized. And if you remember, sp hybridized carbons want to be 180 degree bond angle. But this is forced to be, well, not 180 degrees because it's in the ring, right? So that creates a lot of strain. So not very stable. Right, again, those carbons being sp hybridized want to be 180 degrees, and they're not. So as soon as you make that, it reacts. So another NH2 minus comes in, makes a bond here. Take these electrons, make a lone pair on carbon. And then these electrons, so basically you did an elimination in the first step, and now you're doing an addition. So it's following an elimination addition mechanism. Okay, so then in the last step, that carbon with the lone pair picks up a hydrogen from ammonia, from the solvent, and you remake NH2 minus. So in essence, all you did is took this NH2 and substituted for chlorine. So it's a substitution by a nucleophile, so it's a nucleophilic aromatic substitution, but it's not a straightforward mechanism, certainly not a mechanism like the one we saw up here. It's a totally different mechanism. It goes through this benzine intermediate. So of course we can't tell where the NH2 ended up at with regards to where it started at, because if the NH2 was on any of those 6 carbons, it would be the same molecule, right? But that's not true here, because now all of the carbons are not equal because of that CH3 on the ring, because now you have ortho meta para isomers that are possible for the product. Okay, so what happens in this reaction? So same mechanism. So you have a leaving group on benzene, you have NH2 minus, that's your recipe for benzine, so that's how you recognize it. So NH2 takes the hydrogen off. Those electrons go there to make a triple bond. Chlorine goes off. And you have a benzine intermediate, right? The Y and E, if you remember, that's how you name alkynes, triple bonds. So you have an alkyne in this molecule now. And now when this reacts, well, now these 2 carbons are not equal, right? So here, the 2 carbons are the same for benzine, because of the symmetry of the molecule, but that CH3 breaks the symmetry, and so now the NH2 could attack either carbon. So the NH2 could attack this carbon, and those electrons could go up to make a lone pair on that carbon, which would give you this. And then these electrons would pick up a hydrogen from ammonia, and you would end up with a meta product. Right, but the NH2 minus could have attacked the other carbon, so you could take a lone pair here, and you could have attacked that carbon instead, and then these electrons would go there to make a lone pair to give you this, and then that carbon's lone pair picks up a hydrogen from ammonia, then you would have made the ortho product. Right, so that's a clear indicator that there's not a direct displacement of the chlorine. Because if you just had a direct displacement of the chlorine, since you started with ortho, you would expect to end with ortho. But the fact that you can make this meta isomer indicates that there's not a direct displacement of chlorine, so that would be an indicator that maybe this mechanism of benzine is correct. So sometimes isotopes are used in organic chemistry to help study mechanisms. So in this particular example, so the asterisk represents a carbon that's been substituted with a carbon-13 nucleus. Right, most carbon in nature is carbon-12. So that's about 98.8% in nature, and there's only about 1.1% carbon-13 in nature. So all of these other carbons in benzene would typically be carbon-12. So if you synthesize one that's got a carbon-13 there with a chlorine attached and then did this reaction, then you should recognize you'll get two different products. So you'll get isotope scrambling. You know, why do you get isotope scrambling? Again, if we think about the mechanism, right, this goes here, that goes there, this comes off, and you make benzine with the isotope there. And then when NH attacks, right, the NH2 minus could attack this carbon, or it could attack that carbon, either carbon of the triple bond, so you get two different molecules. And so that's what you would typically be called scrambling, where you get scrambling of the isotope, because it doesn't just, here you started with the isotope in only one position. Here the isotope could either be ortho to the nitrogen, or it could be on the same carbon as the nitrogen, depending on where the NH2 minus attacks the benzine at. Okay, so finally, you could also use trapping experience. So organic chemists are always interested in figuring out the mechanism of a reaction, because if you understand the mechanism, then you can tweak the reaction to try to improve your yields, or understanding the mechanism may help you discover new reactions. So, you know, benzine is such an unstable molecule. Of course, it creates some controversy whether in the literature whether do you really make benzine or not. So there's always there would be experiments done to try to illustrate, that this is a good mechanism and this is the correct mechanism. So one way to study mechanism is to do trapping experiments. If you think benzine is made in the reaction, put something in there that would react with benzine that would give more clear evidence of it. So if you did this reaction, for example, with this 1,3-cyclohexadiene, well, if you make benzine, so NH2 minus, right, we'll pull off a hydrogen and make benzine. And if you make benzine, then that's could be very reactive towards a Diels-Alder type reaction to a 4+2 cycloaddition. And so that's what this could do. This could trap it. So that could go there, these electrons could go there, and those electrons go there in a 4+2 cycloaddition. And if you can isolate this out of your reaction mixture, then that's evidence that you made benzine in the course of this mechanism. Okay, lastly, let's take a few problems just to see if these concepts are making sense to you. Okay, and I'll show you all some of these little twists that you may see pop into exams. So if we started with this material and reacted it with this, so now we've seen several mechanisms of aromatic compounds. We've seen electrophilic aromatic substitution, nucleophilic aromatic substitution, benzine. So which is this? Well, it's not benzine, because that's your recipe for benzine, right? It's NH2 minus and ammonia with some leaving group on benzene. So this is not a benzine reaction. It's not electrophilic aromatic substitution, because that is electron rich. That is a nucleophile. This is nucleophilic aromatic substitution. And there's only one equivalent of it. So what I'm basically wanting to see is, do you recognize which chlorine is going to come off? And so we had made the point that leaving groups ortho or para to a nitro group are facilitated to leave compared to meta. So this is just going to do substitution at the ortho position. Right, so it'd substitute the ortho chlorine and not the metachlorine. And so this is where students get confused all the time. They think, well, is it NO2 a meta director? Yes, it's a meta director an electrophilic aromatic substitution, but this is not electrophilic aromatic substitution. This is nucleophilic aromatic substitution, and the rules are totally different. Right, so it's going to facilitate substitution at the ortho or pair position to the nitro. So that's your major product. Okay, and in this case, again, that's a nucleophile. So this is a nucleophilic aromatic substitution, and we made the point earlier, which is about our leaving group, fluorine or iodine. Fluorine is, so this is going to substitute off the fluorine preferentially and not the iodine. So oxygen comes in, cyclohexane ring is just tagging along and substitutes for the fluorine in a nucleophilic aromatic substitution. Okay, and again, so in this case, so this is a nucleophile. So this is going to do nucleophilic aromatic substitution, and that's going to give you, so sulfur would substitute for the chlorine, and you would get that. But this is a recipe for electrophilic aromatic substitution, right? Back in the first lecture over this material. So what you have to recognize here is if you're doing electrophilic aromatic substitution, then OP versus meta directors is what you have to factor into the equation. So the NO true group is a meta director. So the NO2, so let's call this purple. So it wants to put the next group there, or there, meta to it. And the chlorine, let's see. Is an OP director, so it wants to put the next group there and there, so they want to put it at the same spot, so then that's where your reaction would occur at. And that would be your major product, right? So that's electrophilic aromatic substitution. What did you substitute? You substituted hydrogen for bromine. This is nucleophilic aromatic substitution. What did you substitute? The leaving group for the nucleophile. Right. So when you do nucleophilic aromatic substitution, ortho-meta versus para-director, ortho-para versus meta-directors is not factored in at all. Has nothing to do with the reaction. It's only when you're doing electrophilic aromatic substitution does that matter.